So what we have seen in the previous talk is that the whole system integration is relying on one assumption, is that a stream can always exchange with all the other streams, which in reality is not the case. So we know that, for example, it would be nice to not connect directly the boiler with the process, but you would prefer to produce steam in the boiler and then distribute the steam that is used inside the process. So what I would like to show you is that there is a way to solve this problem in a mathematical way. The idea is the following. So let's assume that you have a process that can be divided, that is divided into subsystems. And let's assume that you would like not to exchange between the subsystems. You know that the exchange can be done via heat transfer units or via the utility. Okay, utility is supposed to be a subsystem which can exchange with everyone, with all the other units. Okay, so we will name it the heat transfer system here. That is going to make the links between the different subsystems. So we know that we have, if we want to do the process integration, we will solve this problem. That will give us the list of the possible heat recovery in the system, but that doesn't have any heat transfer constraints. So we have to modify the heat transfer constraints, the heat cascade constraints, in such a way that we will be able to express the restricted matches. And the way we can do it is by using the following trick. What we are going to do is that we are going to write the subsystem heat cascade as different set of equations. So instead of having one big heat cascade, we will have a list of heat cascades in which we will have to decide how much heat is transferred from this subsystem to the common system, which is the one that is allowed to exchange with all the other. Okay, so it's similar to what I have shown before with the heat load distribution. So I'm going to make finally a subsystem here, which will exchange with itself, okay, and that is going to have a new additional variable that is going to say what is the amount of heat that I'm going to deliver to the rest of the world. Okay, or that I'm going to receive from the rest of the world, and this is a value for each temperature interval. And the rest of the world will have also its own heat cascade with what the rest of the world is going to send to this subsystem, to send to this system, or to receive from this system. So it means that I will have several heat cascades that have to be treated all together. And the flows in the different units that are here, here, or here will be calculated in such a way that there will never be any heat exchange between this subsystem and this one. Okay, now the problem is that when I'm introducing this kind of constraints, I'm restricting the heat recovery. Okay, so it means that if I have not a complete list of system of streams inside in my problem, I will have to pay a penalty. So for example, here, this is what I'm calculating without any constraints. So I calculate here the hot utility flow and the cooling flow, which is needed with those values. And as soon as I'm adding the constraints in my system, I have this situation where the hot utility are much bigger. Okay, and the reason for this is that there is a heat recovery that was necessary, but and that was accounted when I was calculating without constraints, but that is not feasible. So the heat is available, but nobody can use it. Okay, and the consequence is that I will have to pay more in the boiler and therefore more also in the cooling system. Right? So now, to some extent, it's frustrating because I'm adding the constraints, but I have to accept the penalty. Okay, and I have, however, a very nice information now because I have the difference. So I know how much I'm spending without the constraints, and I know how much I'm spending with the constraints. And when engineers see penalty, what they do? They try to find a trick in order to reduce the penalty. Okay, you will never accept a penalty like this. So let's try to find a way. And the way is to use an intermediate stream. So let's assume that this heat exchange was necessary between this hot stream and this cold stream. So this is the heat recovery that is needed. Okay, if I want to set to have the penalty set to 0. Okay, so what I'm going to do is that I'm going to take this hot stream and I have this cold stream. They cannot exchange directly together, but what I can do is that I can, with this hot stream, I can heat a fluid, and then I can cool the fluid here, and at the same temperature, to heat up this one. So the price to pay, and it is represented here. So I have the heat transfer fluid, which is going to be here heated, and then here cooled down. Okay. The price to pay is that instead of having one heat exchanger, I will have 2 heat exchangers. Okay. And the price to pay is that I have to make the fluid circulating. Okay. But there is another advantage. I can add a heater on this loop, and I can add a cooler on this loop, which means that I can have a higher flexibility in my system. Because now the heat load here is not necessarily binding the heating of this one. If this one is not available, then perhaps I will be able to compensate by this one. So my system will be more flexible. So if I know what are the conditions of this, the temperature conditions of this intermediate fluid, then I will be able to calculate to mitigate the penalty. Okay? So the question is, what are the temperature levels? And of course, here I have a hot stream and a cold stream, but in reality, I have a collection of streams that cannot exchange one with the other directly. So what I'm going to do is that I'm going to use a trick or use a mathematical formulation that will allow me to calculate what are the conditions that have to be satisfied by the heat transfer fluids in order to set the penalty to 0. Okay, and I'm going to do it by calculating what we name an envelope, the temperature conditions that have to be satisfied by the intermediate streams. So how do I calculate this value? So I have again the same heat cascade for subsystem A, the same heat cascade for system B, the heat transfer system that is already defined. Okay, and I'm going to add 2 streams for which I will write specific conditions. The specific conditions is that the heat of this one has to be equal to the sum of the heat of this one has to be equal to the sum of the heat of this one, plus another condition that is going to tell me that I would like to, if I receive heat from this one, from whatever size, the hot streams will have to have the lowest possible exergy content, and the cold streams will have to have the highest possible exergy content. And I'm going to add this into the optimization procedure. By doing this, I will calculate what is shown here, the envelope, which is the hot streams that are needed, the hot conditions that are needed by the heat transfer fluid, and the cold conditions that are needed by the heat transfer fluid. And any set of utility that are between this hot envelope and the cold envelope are compatible for doing the heat transfer between to mitigate the penalty. That means that if I have something which is in between the two, then I will be able to mitigate the constraints of the restricted matches. Okay, so the summary is the following. I'm using the mathematical programming formulation in order to calculate the conditions that have to be satisfied by the intermediate fluids, so that I will be able to define the intermediate fluids. And as soon as I have identified this one, for example, so here it's from 25 to 80, I will propose this and I will solve the problem with this formulation now, without the additional elements in the system, and I will calculate the flow that has to be used in the heat transfer system. By doing this, I will be able to calculate finally what are the flows. Now, the reason why I'm using this envelope is that intermediate fluids can also be used in order to do cogeneration. What does it mean? It means that I can produce high pressure steam, expand the high pressure steam in the turbine, and use the condensation elsewhere in another subsystem. Okay, so it means that at the same time, I'm going to not only remove the penalty of the constraints, but I'm going to introduce the cogeneration at the same time. Okay, and by having the envelope here allows me to define where I have to place the conditions of the steam utilization, for example. And here, just to show you why it is important, a priori we would have used only the steam at 2 bar, but it appears that the 2 bar would not allow to reach this temperature. It means that I would have a penalty if I would have used only 2 bar. I have to add another level at 7 bar in order to mitigate all the energy penalties in the system. Okay, and this is what is shown here. So this is the solution when I have added the steam in the system. So I'm going to produce 80 bar steam because the demand was very high, so the envelope was very, very high. I have to add the steam utilization at 7 bar. I'm adding the second one at 2 bar, and here you can see that, well, they are compensated one with the other, but they are calculated. So it means that I have a flow where I'm taking the heat in on one subsystem and transferring it into another subsystem. But by doing this, then I have been able to mitigate the effect of the restricted matches. I have more streams, okay, but now I have no penalty. Something which is also important is that, especially when you are using intermediate fluids like a heat pump, so a heat pump is in fact a cycle. Okay? So it means that the intermediate fluid can be used as a way to transfer heat from one place to another one. Okay, the same as for the steam cycle. It means that I can use a heat pump in order to take heat in one subsystem and drive it in another subsystem. Okay, so while we could say that it's not enough because I have just calculated the conditions to be satisfied by the temperature, but it's not by the intermediate heat, but it's not necessarily that I have taken the right decision. So it's possible to add a next dimension to the optimization by saying, okay, we are going to optimize the conditions now. We know we know how they are framed, but I would like to verify that they are the best conditions. So, for example, the temperature difference is going to define the flow, and the flow is going to define the pumping cost. Okay, so the bigger the temperature difference, the lowest is the flow, the less is the cost for the piping, for the pumping. Okay, so what we can do then is to do the same approach as the one that Alberto has presented for the with a V-level approach. So on the one hand, we are going to decide at the top level what are the temperature conditions. As soon as I know the temperature conditions, then I can apply the linear programming approach in order to calculate what are the flows. From the flows and the temperatures, I can calculate what is the operating cost, but also what will be the investment cost, and then I can loop with the optimization to calculate what are the best temperatures of the heat transfer fluid. And this is an example of what is done here. So what you can see is that on the one hand, I have how much it costs, and you can see that it is not really sensitive here. It's the cost of the heat transfer fluid, and this is the operating cost. You can see that it's not neither really sensitive there. It's mainly because it's just a heat transfer fluid, so it doesn't cost too much. But at the end, we are able to optimize and to see where is the best compromise in the conditions of temperature of the heat transfer fluid. So for example, here, the 0.1 corresponds to high operating cost and low investment, and it goes from 49 to 69, while this 0.4, for example, is doing the biggest temperature difference, higher investment but lower operating cost. And this one is finally not so far from what I would have done manually, intuitively, which was doing the biggest temperature difference that I have seen in my calculations. Okay, so at the end, this is also perhaps a message. Sometimes just graphically we are much better than a very nice optimization tool. So don't forget to just include the what you know out of the problem in the method. Now, once we have the definition about the flows, then you can do the heat load distribution by imposing that some integer variables are now set to 0, because all the heat exchange that are forbidden are by definition set to 0. So it means that you can do the heat load distribution, you can do the heat exchanger network design by having reduced the number of possibilities in the system, because you know that they are set to 0. Okay, and this allows you to have solutions like this one, where we know what are the heat, what is the heat that is exchanged between the different subsystems. And just to show you that it makes sense in this example, so this was the situation without the constraints. This was the situation calculated after having introduced the constraints, and this is the situation when we have added the constraints and the heat transfer units. And what is the difference is mainly coming from the fact that we have a lower operating cost because we have introduced at the same time the cogeneration unit that is used as a heat transfer. Okay? Right. So this is one application. The other application that is important is the multi-period problem. But I will perhaps show this in more detail this afternoon.